Okay, so without further ado, our first speaker of the workshop is Alba Cervera-Lierta with a lecture on variational quantum algorithms. Alba probably doesn't need an introduction at this point, but nevertheless, let me tell you that she did her PhD on quantum computation and information at the Universitat de Barcelona, and then a postdoc at the University of Toronto in the group of Alana Spuruguzik. She is now a senior researcher at the Barcelona Supercomputing Center in the group Quantic, and since 2021, she's also the coordinator of the Quantum Spain project. Alba, thank you for coming, and whenever you're ready, the floor is yours.
Okay. Yeah, let's go more analog. So thank you very much for inviting me to do this talk. Sorry that I have a very bad voice now due to the air conditioning and all of this. So I'm the coordinator of Quantum Spain, which is also a co-organizer of this workshop, and I will talk about it a little bit later at the end. So I would like to give a very general introduction of variational quantum algorithms. And for that, I was thinking, because that will be quite a long introduction to all of this topic, so maybe we can make a break at the middle, like 10 minutes, so we all go to the bathroom or whatever you need. So I will just ask you if you are okay with making the break or just continue and finishing a little bit earlier. So it depends, it goes on you. So this is the outlook of my talk. So it will motivate why are we working on variational quantum algorithms, and also what kind of things can we do to extract the most from current term quantum computers, which is basically the topic that we develop at BSc together with quantum emulation. So let me start. So I will assume that most of you know about quantum computing, of course, and what are the basic principles of this technology. Hello. Let me remind you a little bit of what are the basic ingredients to build a quantum computing device. So of course, it's based on the superposition and entanglement, etc., of qubits, which are the basic units of quantum information. There exists also qubits, which is the dimensional units of quantum information, but most current term quantum computing based on the binary representation of a qubit. And for that, technologically speaking, we need some quantum device that is able to hold these quantum properties like superposition and entanglement. So we can have interference eventually to lead to this long-standing quantum advantage. And also we need some kind of physical device that can define very well two levels, like the 0 level and the 1 level. And this is very important because naturally quantum systems have more than two levels, like the quantum harmonic oscillator or many other kind of devices that can have these properties. But it will be very important to have a very clear definition of what is a 0 and what is a 1. And this is one of the main reasons why, for instance, for superconducting circuits, those of you that know a little bit about that, we use non-harmonic quantum oscillators, because we need to separate the 0 and 1 level from the rest of the levels of the spectrum. And at the same time, if you don't do that properly, that will be a very high source of error in these quantum devices. Then we need to isolate these 0 and 1 levels, but at the same time, it goes up and on and off the microphone, just to let you know. So yeah, it happens that we need to manipulate these levels properly. Otherwise, we cannot operate and perform quantum operations like quantum gates. And on top of that, we need a scalability. So we need to have more than one qubit, not a single one. So that could be a very big issue depending on the technology, because we have several technologies that allow for this kind of devices, and some of them are really, really good to have a very good qubits, but they only can have only 1 or 2, and others are really, really good on scale properties and of the qubits as the other platforms. So some of these examples, we have superconducting circuits, we have photons, we have colatons, we have trap ions, we have MB centers, we have quantum dots, we have several types of technologies. So in contrast to classical computation, quantum computation have different physical platforms to be designed. And on top of that, I would like to remind quantum computers are not only quantum devices. You also need classical software. So what is quantum in a quantum computer is only the hardware part. we need to control this hardware part from the software that is controlled, as you know, from your laptop some of the time. So basically, we will have some libraries that are made on Python, for instance, C++, depending on the language, that sends a list of instructions to the hardware that contains qubits, quantum processing unit. So then the result of the quantum computation is returned to the classical part, and then we can interpret the result, we can post-process the result, and then maybe send another batch of instructions to the hardware. So this loop will be really, really important in quantum computing. We will need it for sure, so there is no quantum algorithm that will not require from classical pre or post-processing, and that's why it's so important to link these quantum devices to classical devices. So this is the theoretical framework, but we don't have proper quantum computers yet. So as most of you know, we have now of quantum computers, and these prototypes are made of 50 to 100 qubits. They low. No. Hello? No. They don't have we cannot perform quantum error correction. So this is a big trouble if you want to implement well-known algorithms like short. No, really, what is happening? So okay, can you hear me anyway, with or without the microphone? Okay, so just keep going, and I'm sure maybe the YouTube people will not listen it properly, but okay, they should come. So we don't have quantum error correction. We have technological platforms. And so what can we do? So most of these well-known and with some advantage quantum algorithms require from perfect operations and perfect qubits, but we don't have that. So what we can do, at least, is to see what kind of other applications can we develop with current and prototypes. So basically, we have to be creative, and we need to find ways to extract the most from current and quantum algorithms. So this is a step towards this fault quantum computing era in the future, once we can implement quantum error correction. But at the same time, we are sure, or at least I'm sure, that we will learn a lot of physics and a lot of applications at the same time with current time devices. So this is called the noisy intermediate scale quantum computation. So this is a very coined term in the field, NISQ, and it's defined in this term. So basically, anything that you can do with current time devices that do not require correction. So how can we extract the most of these devices? So as I was mentioning before, a quantum computer requires from a classical computer to pre and post-process the results. So a way to precisely close this loop and trying to link all these quantum subroutines to the classical ones. So this is hybrid quantum classical computation. And one of the main representatives of this kind of computation are the variational quantum algorithms that I will explain right now. So on top of having all these different technologies, we also have different models of quantum computation, and it's important to stress this out, because depending on the technology, some technologies are more suitable from some type, and others are more suitable for another type. So I would like to also highlight the classical techniques that are not quantum per se, but they are also very linked to quantum computing and very important. And these are the quantum-inspired algorithms and all the techniques related with HPC quantum simulation. So basically, there are many, many things that we can do related with quantum computing and with quantum simulation with a classical device, because some of the systems can be solved efficiently or can be simulated efficiently. For instance, if they don't require a lot of entanglement in the middle of the process. So these are called, these techniques are called tensor networks. They are really important since the more than 30 years now, but now they are acquiring a different status, because now that we have high performance computers like supercomputers that can simulate very large batch of quantum of qubits, now we can apply these techniques, and on top of that, we are discovering new ways to extract information from quantum devices by only performing classical simulation. And a very good example of the power of these techniques, and I will not focus my talk on this topic, but I would like to highlight it, because this is also something that we do at BSc. But some very good example is the recent result from IBM, which was a very important result related with quantum computing. They performed a very large simulation in 127 qubits, which is super impressive at that time of the level of technology. They apply some error mitigation techniques that I will mention later. But then what happens is after only 2 weeks, a bunch of researchers from different groups, they were able to simulate these results, so 127 qubit, which is very, very large quantum computation, in even with a laptop. So it's impressive the level of sophistication of these classical techniques, and that's so important to keep an eye on them, because sometimes you claim quantum advantage that you don't have quantum advantage after all. So that's something really important, because this line between quantum and classical advantage is not static at all, especially now that we have more and more powerful supercomputers. So then we have the purely quantum computing paradigms, and one of those is analog quantum computing. So here I include quantum simulations, which basically are based on cold atoms. But I also like to include annealing or adiabatic quantum computing, because it's another way of performing quantum computation that is universal. It can be proved theoretically that is universal. And it's also suitable for quantum simulation and to solve optimization problems. And then we have the well-known digital quantum techniques, especially the most known one, which is quantum computing with circuits. This is the most similar one to classical computation, and is the one that I will focus my talk. But then you should know that there are other ways, like one-way or measurement-based quantum computing that goes the other way around. So quantum computing with circuits, you start with a product state and you entangle the circuit and you apply operation, and at the very end you measure whatever you have at the circuit that you have at the end. But in measurement-based is the other way around. You start with a very large entangled state that normally is called cluster state, and then you perform a set of measurements, and depending on the measure, you obtain a final result, and it's also another way of performing quantum computing. So just to let you know that there is life beyond quantum circuits. So let me now go to the main point of my lecture, which is variational quantum algorithms. All these slides will be available, so you can check the references therein, and you can, if you are interested to know more details about this. First of all, it's really, really hard to design unless we have some kind of receipt. So for instance, for well-known algorithms like quantum phase estimation, quantum Fourier transform, etc., we have a receipt to create the circuit, and we know which gauge we should implement to end up in the final result. But what happens with other kinds of simulation? So of course we can do Trotter steps, we can do many things to perform quantum simulation, but at the same, in general, it's really hard to find the unitary operation that drives you from one point of the Hilbert space to another. And Hilbert space is incredibly large, as you know, so it's exponentially large with the number of qubits that we want to simulate or we want to compute with. So it's really hard to find this path unless you have a very clear receipt, which is not the case in most of the applications. So the question is, how can we find the path in the theoretical one? And on top of that, is that path something that we can implement with current term technology? So imagine that we have a quantum circuit that looks like this. So each of these boxes is a quantum operation, as you know. So this is an ideal circuit that I perform a Hadamard gate, I perform a control Z gate, a rotational Y gate over pi over 2 angle, because it's something that for some reason I want to implement, and so on. So this is very nice, but this is not the reality. That will not happen once I implement that on real hardware. Why? Because my hardware have errors, so this rotational Y gate will not be exactly a rotational Y gate, obviously. Will be something hopefully close to that gate, or maybe not even close, depending on the errors. So we cannot run well-known algorithms like Grover, transform, etc. So that we cannot also run algorithms that require a lot of gates, because the coherence of qubits is limited. So we don't have very long coherence times. So we have like some amount of time to apply whatever you want to apply. And after that, you lose all coherence. So basically, whatever you do after the coherence times is completely lost, and on top of that, so that's a very very clear limitation. So what can we do, or at least an idea is, okay, why if I'm more, general, and I decided to apply some parameterized gates that depend on some parameter, and I will just try to find the optimal values that my hardware can implement. So imagine that depending on my platform, I cannot implement a rotational Y gate over pi over 2, but I can implement some rotational gate, and then I will just try to find the I'm interested in. So basically, variational circuits are this kind of circuits. So my quantum creates variational states that depend on some parameters, and I will try to create a cost function that will optimize on top of these parameters. So with that, we can run algorithms that do not require specific quantum gates, and I will describe some examples of which kind of algorithms are those. And at the same time, I can just limit it how many gates. So I can just put some layers of quantum gates, and after that, I will just try to optimize on top of only those gates and not require more of them. So the question is, how can we design algorithms with that flexibility in gates and number of gates and which kind of gates I use? So these are the main schematics of a variational quantum algorithm, also called hybrid quantum classical algorithms for obvious reasons because of this part here that I will explain. So basically, we start with some initial state, which is normally 0, 0, 0 state, and maybe some kind of pre-processing part that implies to apply some X gate or whatever, but you can assume this is a product state, something easy to implement and easy to initialize our quantum circuit. And then we apply a set of gates that form the parameterized quantum circuit, okay? So at this point, assume that this is a black box that depends on some parameters. So after these parameters are applied, or these gates are applied, I have some output state that, of course, will depend on these parameters. So with this output, I can compute some expectation value of my objective function. This objective function, in general, will be a Hamiltonian that I want to compute some ground state, but it could be other things. So I will also explain this and make some examples. So once I have this expectation value, on the first run, these parameters are completely random. So that will be some random number. But this is a classical number. So I can plug this number into a classical minimizer. So basically, I can use well-known classical techniques for optimization and to find minimum. This is just a number. So this is after this point here, everything is classical. So I put this number here, and I put maybe, I can compute also the gradients of all of these that will also be numbers, classical numbers, that will enter into this box. And with this optimization subroutine, I will have a new batch of parameters. Then I change these parameters in my parameterized quantum circuit, and I run the algorithm again. So there is a very well-known theorem in quantum mechanics, which is the variational principle. So whatever you compute here, so this expectation doesn't work anymore. This expectation value of the Hamiltonian, whatever you compute here will be an upper bound of the ground state. So after iterating several times, hopefully, and I cross my fingers because there are many things, many problems that could arise after that, I will converge towards some some minimum energy. And this energy, hopefully, is close to my ground state energy of the objective function. So this is the main schematics of a variational algorithm, and we will enter into detail of each of these boxes. So let's start with the parameterized quantum circuit. So as I was mentioning, now it works. As I was mentioning, the state will depend on the parameters that I plug into this into this parameterized circuit. So basically, my quantum operation will be this U that is applied on a product state, on the 0 state, which is the initial one. So, and I have to minimize all of this part according to these parameters of my circuit. So there are some assumptions here, and the most important one probably is that I'm assuming that my parameterized quantum circuit can represent the solution. And this will be linked to expressibility of quantum circuits that I will also mention later. And another very important assumption is that I can converge towards the solution. I can get trapped very easily to a local minima, and that's the thing that will happen probably. And this is another issue to be solved with variational quantum algorithms. And on top of that, I'm doing all the being as because I couldn't implement well-known algorithms with current and hardware. So whatever I propose here, it has to be suitable to be run on a NISQ computer. So how can we design this quantum circuit? So basically, there are two strategies. The first one is the problem-inspired PQC ansatz. So basically, it's an approximation of the solution by imagine that we apply Trotter steps, those of you that know about what is Trotter expansion, or there are other kinds of answers that I will give you an example when we talk about the applications, that they are inspired on the circuit or the Hamiltonian that we want to simulate or we want to compute a ground state. So basically, I can do that, and this way I'm trying to be as close to the real solution. The problem of these problem-inspired ansatz is that in general they require high circuit depth, so they require gates, and that's something that I cannot do with current term devices. So they are not as hardware friendly as possible, and the number of gates is in general quite high. So in the end you need these very large operations that unite. It's complicated. So a strategy that I think it was IBM that had the idea to create was the hardware efficient ansatz, which is, okay, I cannot do this, but I can just kind of create some in a layer structure. So as much layers I apply, the more sophisticated will be my circuit, basically. So this is good because it's low circuit depth, the number of gates, I can keep the number of gates as low, and it's hardware friendly because I also follow the connectivity on my quantum chip and so on. The problem is it's an heuristic ansatz, so maybe I'm not creating the necessary operations that I need to simulate my problem. So, but on the other hand, it's hardware efficient, so it's good. So there are mainly these two strategies. Let's move to this objective function must encode problem. So in general, will be a Hamiltonian, like some molecule. I want to compute the ground state for some reason. But something important here is that I can only measure expectation values of Pauli strings. So whatever you want to simulate, you want to compute with a quantum computer, you need to represent it with Pauli strings. And these Pauli strings are the ones that I will be able to measure in my quantum computer. So basically, our Hamiltonian has some number of these Pauli strings, and each of those will be a separate circuit to compute some expectation value, and at the end, I will just plug everything together. So the problem here is like, imagine that this M, which is the number of Pauli strings, is really, really, really large, or it scales exponentially for some reason. Then you lose completely any quantum advantage because at the end you need to compute an exponential amount of expectation values. So it's something to keep in mind because depending on the application, sometimes it could be very simple or very nice, but then you realize that this M is super large. So again, there is no advantage here. And another ways to create this objective function is, for example, computing fidelities or distances between two quantum states, the one that I'm computing with my circuit and the one theoretical one that I want to approximate. And that will be the case, for instance, for quantum machine learning, and I will give you a particular example. With this measurement, I will just go through it very quickly. So you can only measure expectation value of sigma z operator with a quantum circuit. So basically, how many zeros and how many ones are you obtaining at the end of your computation? So if you need to compute expectation value of sigma x or sigma y, you need to rotate your qubit at the very end, or your quantum state at the very end. So this is something also to keep in mind, that it's not automatic that you can compute the expectation value of any Pauli string. Sometimes you need some final layer of rotations in the quantum circuit. And finally, we have the classical optimization. So as I was mentioning, this is something completely classical, but if I want to use gradient-based methods, for instance, I need to also compute the gradients with my quantum circuit. And for that, I can use things like the parameter shift rule, and there are other ways to compute gradients. This is mostly the most used one or the most easy to understand one. But basically, that means that I need a separate circuit to compute each gradient. So imagine that my quantum circuit, my variational circuit, has, I don't know, 100 of parameters. Then I need to compute 100 of gradients at least. So these 100 of gradients are separate quantum circuits. And on top of that, I need to sum all the different circuits that allow me to compute the expectation value of each Pauli string. So if you keep going, you can see that the number of circuits that I need to implement to find a final solution, could be very large. So something very important also in variational algorithms is to keep these parameters as low as possible. Or an alternative is to use gradient-free methods like genetic algorithms or even reinforcement learning. So just keep in mind that when someone presents to you a variational quantum circuit with, I don't know, I need to optimize 1,000 parameters. That's easy for current terms classical methodologies. Like 100 parameters is not so much. But keep in mind that maybe that's only a simulation. If I want to do that on a real quantum computer, I will need 100 or 1,000 different quantum circuits on top of whatever I have to do. So that's a lot of circuits, especially in current term devices.
Alba, ¿prefieres probar con este?
Ah, vale.
Okay. El micro, lo siento.
Let's try it. La tercera va la vencida, ¿no? A ver, así. ¿Hola? Sí. Vale. No, mejor, porque si no, nos volvemos locos. Okay, so what are the applications of these variational quantum circuits? So I will just go through these three main examples, but keep in mind that this methodology is super general. So in the end, you can basically adapt any application to a variational quantum circuit. So if you are interested in something that goes beyond these examples, there's probably a way or someone has tried that before. I'm not sure. Okay. So let's move to what can we do beyond variational quantum circuits to extract the most from current term devices in NISQ. So this is something very general that can be applied to other kinds of quantum algorithms, not only variational. First of all is the quantum error mitigation. So keep in mind that when we talk about error mitigation, there are, in my opinion, two ways of perform that. One is purely post-processing, so classical post-processing, and another one is more related with the hardware. So how can we engineer the gates in the best possible way? So starting with the first one, which is the theoretical, I call it theoretical post-analysis. Maybe it's not the right wording, but I mean that all of this is after I measure my quantum circuits. So some of these techniques are based on the fact that I want to modelize the noise that my quantum circuit has. So for instance, the most easy way to understand this is with zero noise extrapolation. So instead of running our unitary circuit, I run several times unitary and the dagger of this unitary. So theoretically, this is just the identity, so nothing should change in my quantum circuit. But in reality, what happens? Each of these unitaries introduce some noise into my quantum circuit. So after applying this multiple times, I can try to extrapolate what is the so I will see some decaying of the solution, of course, because as much noise as I use, the solution will be worse. So I kind of, once I have this curve, I can extrapolate backwards of what will be the theoretical solution with no noise. So that's why it's called zero noise extrapolation. This is a very, direct way to try to mitigate errors, but there are others. So for instance, we have a stabilized Bayes approach, which for instance could be that imagine that my solution only have some parity in the qubits for some reason. If I measure a set of qubits that doesn't have this parity, then I can discard this solution because it's unphysical. And then we have more sophisticated techniques like probabilistic error cancellation. And these are, for instance, one of the techniques used by IBM, and I think it's probably the most used one and the most reliable one, which basically I'm trying to modelize the noise in my hardware, so I try to cancel this noise using more quantum gates. So once I know more about the noise of my hardware, I can try to implement in the middle some quantum gates that will cancel some part of this noise. Then we have what I call experimental mitigation. So for instance, each time that I run some quantum circuits in hardware, these quantum circuits are decomposed into pulses, are decomposed into hardware operations that run on the hardware. So when I do that, I can do things more sophisticated, like dynamical decoupling, which is trying to isolate one qubits from the others that doesn't suffer from this quantum operation in order to mitigate crosstalk. Or I can also use pulse shaping techniques, so changing the pulse shape in order to extract the most from quantum circuits, and so on. So basically, there are many ways to improve the qubits operations. And these are purely hardware operations. So it's like, this is happening while you are running your quantum circuit, while the other ones, the post-processing ones, are something that after you measure everything from your quantum circuit, you made some, you treat your data somehow in order to extract the most from it. Then another really big problem in variational quantum circuits is the so-called barren plateau. So as I was mentioning, a variational circuit have some parameterized quantum circuit that depends on several values. And the problem is, once I try to minimize a certain cost function, it's really easy that I get trapped in a local minima. Actually, it's worse than a local minima, because what happens is, if I see what is around me, if I'm one of these points of these circuits, I see that all the parameterized space is flat. So there is no way that my gradient can guide me towards the solution. So that's why they are called barren plateaus. So that happens. This is related with unitarity designs and many other things related with the exponentially large Hilbert space that you have to explore, and also the randomness of the circuit. So basically, it happens if you start at a random place, which is most of the cases in variational circuit. Just start with some random values at the very beginning, and then depending also on the cost function that you are using. So some people are trying to mitigate these barren plateaus or to eliminate them by using very specific cost functions. So it will be very important not only to create a very sophisticated unitary circuit, but also trying to think which cost function will be better in order to avoid these barren plateau problems. So there is some people, especially there is this group here, the Marco Cerezo et al., at Los Alamos Laboratory in the States, that are super experts in barren plateaus and trying to find methodologies to avoid them. Then we move to another issue, which is the expressibility. So as I was mentioning, we are assuming that our quantum circuit can be represented with my parameterized quantum circuit, which in the end is just an ansatz, it's just a guessing. So ideally, this is my initial state. This is my parameterized quantum circuit that guides me towards the solution in the immense Hilbert space that is exponentially large. So that's the ideal case, but what happened probably is that I'm here, this is my parameterized quantum circuit, and my solution is not there. Not only is not there, it could be very far away, because if my solution is here, well, at least I can get really close. But some of the cases will not even be that, unless I'm using, very special techniques. So expressibility means trying to find the most general quantum circuit that will allow me to explore the Hilbert space in an efficient way, and also to find the solution. What happens that you can easily end up into a very, very large quantum circuit. So there is a trade-off between expressibility and trainability, because in the end I can use a general unitary gate and I can decompose that, but that requires an exponential amount of real parameters that I will need to optimize afterwards, and I have problems like barren plateaus and like computing gradients and so on that will limit me. So basically there is a trade-off between high expressibility and untrainability. So if I have to train, 1 million of parameters, then even if it's super expressible, it will not be a useful quantum circuit after all. So I also recommend this recent paper where they explore this expressibility versus trainability issue. And basically their conclusion is you need to sacrifice expressibility towards trainability. So in the end, what means, at least in my experience, is like hardware efficient ansatz, like the ones that I mentioned before, that are more hardware friendly and so on. They are not the best ansatz to be run in sophisticated applications. Why? Because they will need a lot of parameters in order to achieve high expressibility and find the solution, which is something that can lead to untrainability. In contrast to that, what people is doing is trying to find these problem-inspired ansatz that only have a few parameters, but they explore the Hilbert space in a more sophisticated manner or more cleverly. So that's what people is abandoning these hardware-efficient strategies, just to let you know, because this leads to untrainability most of the time. And finally, of course, there are other things to squeeze the NISQ lemon, but something very important to keep in mind is you are doing all of this, but at the end you need to implement that in a real quantum computer. So that means you have to follow several steps. You start with a theoretical circuit. You have to decompose it into basic gates. So basically, not all platforms can implement any possible unitary operations. So basically, you can only apply 1 and 2 qubit gates. And in some platforms, not even all 2 qubit gates. Sometimes you can only apply the control not gate, not the, the control Z or the swap gate or whatever. So it's something important to keep in mind. On the other hand, we have some well-known theorems like the Solovay-Kitaev that assures you that there is a solution to this decomposition. So basically, there is an efficient way to create any quantum gate. The problem is this is an existence theorem, so it doesn't tell you how, it just tells you that it's possible. So that's not very useful, but at least it's kind of reassuring that, okay, it should be some way, so I can make some effort trying to find the efficient representation of my quantum circuits. Then we have another theorem, which is the Gottelmann-Needle theorem, that is related with this quantum simulation, classical quantum simulation that I mentioned at the beginning, which is that if you only use certain kind of quantum gates, which are the ones that belong to the Clifford group, which is Hadamard gate, control node, the Pauli gates, and so on. These kind of gates, if your circuit only have those, everything is simulated efficiently with a classical computer. So of course, once you have your final circuit, you have to check which of these gates are not Clifford gates, because that gives you a hint of how hard will be to simulate that with a classical computer. If you only have a few of them, probably whatever you are trying to do, you don't need a quantum computer. You can do that efficiently with a classical computer. So it's something also to keep in mind once you do this native gate decomposition. And then I highly recommend all the theoreticians or people that wants to focus on theory in this room to talk to the experimentalists and the other way around. Because me as a theoretician, especially if I have to design a parameterized quantum circuit, I don't care about using control node gate or swap gate or I don't know, or Pauli X gate. I don't care. So just give me whatever are your ingredients, and I will try to find what is the best quantum circuit. So it's very important to know what are the limitations in the hardware, because to you as a theoretician, you can kind of adapt to whatever you have in hand. So some of the technologies are more suitable for some kind of gates, others are more suitable for another one. So you can kind of design your quantum circuit from scratch, taking into account what are the basic ingredients of the hardware. And this is also related with the topology of your circuit. So except a few implementations like trap ions and Cole atoms that allow from all-to-all connectivity, also at the expenses of everything is much slower because you have to move atoms around. But except of these platforms, the other platforms like superconducting circuits, they have a very limited connectivity between qubits. So basically these are some of the examples of IBM devices, the Google device, and so on. So that means that if you want to perform an operation between this qubit here and this qubit here, you need to apply swap gates to change to exchange the quantum state, and then apply the operation, and then undo the swap gates. So that's a lot of gates on top of whatever you have to run. So it's really important to adapt your quantum circuit to the qubit topology or qubit connectivity. This is called the mapping to qubit chip technology problem, or the routing problem, and so on. This is an NP problem because it's like a graph matching problem. So that's why sometimes when you design a quantum circuit, you also keep in mind what is the connectivity, the final connectivity of the chip, to try to avoid the use of extra swap gates. And finally, you should also keep in mind that all of this is theoretical, but then you go to the hardware. So the hardware are not quantum gates. Quantum gates are something abstract, something nice, something mathematically. But then what really happens in the hardware are pulses. So basically these gates are decomposed into physical operations that go to the hardware. So if we are optimizing on these parameterized circuits, which are parameterized gates, why not going directly to the core of the problem, which is parameterizing the pulses? So parameterizing the shape of the pulse, parameterizing the frequency, parameterizing the amplitude, the time, and so on. So these are called sometimes control variational quantum eigensolver. It's much costly to be run, to be honest, but at the same time it goes to the core of the problem, which is, okay, I don't care about these very abstract representations called quantum gates. I go directly to the hardware and try to optimize on top of this hardware. So now my second part of the talk, I will review the three main applications and also the quantum HPC integration. So I'm not sure how is the time right now, but maybe we can stop like a few minutes and take a break, if that's okay for everyone. Yeah. Okay, so we can go back in 10 minutes or so. Okay, let's try again with this microphone. It seems like now it works well. So I will just keep it in my hand in case I have to turn it off. So, okay, let's now move to the applications of these variational quantum algorithms, and I will start with probably the one that gave the name to all variational algorithms, which is the variational quantum eigensolver. These are some of the resources that you can check. Of course, there are many, many, many more, and all reviews about variational, you will see BQE for sure. So BQE was initially proposed to solve the electronic structure problem. So this is a chemistry applications, and let me review it quickly. I'm not a chemist, so I will just go through it very quickly to show the motivation. So basically, something very interesting for chemistry is knowing what are how are the electrons located in the molecule or in the atom. So as most of you remember from high school probably, we have the electrons cover the electronic structure of the atom or molecule, and depending on the level or where are they located or in which band and so on, the chemistry properties change and are different, and we have a metal or we have a gas or we have other things. So basically that means that we have some Hamiltonian, the molecular one, that can be split into nucleus and electrons. Of course, this is the Born-Oppenheimer approximation. This is the most used one. And the wave function, therefore, can be factorized as well. So what chemists care about, or at least for these particular problems, is the electronic structure problem. So only focusing on the electronic structure part. And the Hamiltonian looks like this. So we have some kinetic energy of the electrons, some interaction electron nucleus, and some interaction between electrons. So this is a Hamiltonian that can be solved using different techniques in quantum chemistry. So basically, these techniques are called Slater determinants. So what you need is so if we only have one single electron, this is located in the level S, P, D, F, and so on, if you remember chemistry in high school. But of course, that's much more sophisticated in reality. So basically, we have what is called molecular orbitals, in a similar way as when we solve the hydrogen atom, but with molecules basically. And the combination of different wave functions of these orbitals, it's called Slater determinants. So in the second quantization, which is everything is much easy to be represented, it will look something like this. Of course, this is a very direct approximation and representation, but it's to me it's easy to understand it in these terms. So we have some electronic wave function, and we have several orbitals. And the focus space means that I have a 0 if this orbital number 1 is not occupied. I have a 1 if the electron is in that orbital, and so on. And I have k orbitals. And each of these orbitals are combined in a superposition according to the Slater determinant with some coefficients here, okay? So first hint, if the number of orbitals is large, that means a lot of qubits, okay? Because of course I will use this representation with qubits. So what happens sometimes in chemistry is I need a lot of, I need high precision measurements or high precision results, the chemistry accuracy. And that means a lot of orbitals, because as much orbitals as I include, the more sophisticated is my result. But that will mean a lot of qubits. So using variational algorithms or quantum simulation, you don't directly assume that everything will be much more efficient, because maybe I need an exponential amount of qubits if I use an exponential amount of orbitals. So just keep that in mind, because we are improving some things, but others are also still very, very inefficient. So this Hamiltonian, the electronic structure Hamiltonian, can be written in this second quantization using some Hamiltonian of this kind, which is A daga A are the creation and annihilation operators. That means I add an electron in the orbital P, I remove an electron in the orbital Q, and so on. So as you can see here, this term is called the single excitation. So one electron moves to the orbital Q to the orbital P, and that with all the orbitals. And I can also include the double excitation. So two electrons jump from one orbital to another two orbitals, and so on. I can add triple excitations, four level excitations, and so on. And that's why it's called the coupled cluster. This is related with how I represent everything with this creation annihilation operators. Single, double, model. I can also have single, model, triple, and so on and so forth. In that case, for this example, it's enough to just consider up to double excitations. So this is still a classical quantum chemistry, okay? So these coefficients here come from the Hamiltonian decomposition, And these are sometimes computed using some Monte Carlo methods, some integrals, and so on. So still, these coefficients, I will need to have them beforehand in my post-processing part. So because I cannot measure creation and annihilation operators with standard quantum computers, I mean, maybe if I use photonics, it's, the mapping is better, but still, it's not the common thing. So what I need is to translate these operators to Pauli operators. Sorry for the bad quality of the image. And I do that using what one of the well-known transformations called Jordan-Wigner. There are others. There is the Bravi-Kita-F, for example. It's another one. And there are other examples. But basically, it maps its creation annihilation operator to Pauli strings. So once I do this, which is a very simple transformation, everything is written in terms of Pauli strings, of 1 Pauli string, 2 Pauli strings, and 3 Pauli strings, and so on. And each of these Pauli strings is something that I can measure in my quantum computer. So, okay, I have all the ingredients. Keep in mind, again, let me remind you that these H coefficients are computed using Monte Carlo methods for integrals that come from the original Hamiltonian. So still, I need classical computing here to obtain these coefficients, but then I just go to my quantum computer, I measure the expectation value of each Pauli strings, and once I have all these numbers, I plug them together, and I have my ground state energy. Okay, I have all the ingredients, so what can we do to compute these expectation values? I need some wave function, of course. I need the ground state wave function to compute these expectation values. So I can use, which kind of ansatz I can use using a variational quantum circuit. Oops. So what the original VQE proposal tried to follow the classical quantum chemistry methods, which is this unitary coupled cluster ansatz, translated it to a quantum circuit. And the idea is the following. So I have this Hamiltonian, the unitary coupled cluster single-double Hamiltonian, and I will try to approximate it with a unitary operation, making the exponentiation of this Hamiltonian. So the exponentiation of some hermetic matrix, it's a unitary operation. So it's something that I can run in my quantum computer. So it will look something like this. So I start my initial state, instead of the 0000 state, I can use the Hartree-Fock approximation. So Hartree-Fock is the first level approximation of all these orbitals, which is each electron is in a different orbital and there is no superposition here, for instance. So this is the first order, and in terms of my qubits, it will be a 0, 1, 0, 1, 0, 0, 1, whatever. So it's a product state, something easy to prepare in my quantum computer. And on top of this Hartree-Fock, which is the first level approximation, I use this operation, which is this unitary coupled cluster single-double ansatz, where each of these operators here, T, are the different coefficients of my Hamiltonian. So basically, this coefficient here, the second coefficient, sorry, this works sometimes, and so the first one, the second one, and so on, okay? So here I write them in the creation and annihilation operators, but I use the Jordan-Wigner transformation again, so this can be translated into Pauli strings. So remember, in case that you don't know, let me explain to you that the exponential of some Pauli string, it's a unitary operation. For instance, the exponential of I theta sigma x is the rotational x gate. The exponential of I theta x gate is a 2-qubit gate, and so on and so forth. So once I have this kind of what is happening? Alarma de incendios, quizá. Yesterday I was walking around and there was this alarm. That adds more dramatism to all these things. So let me take this alarm to say, okay, careful, because because in the end, if I have a lot of these Hamiltonians here, so this sum has a lot of terms, that means exponential of this term, exponential of the second term, exponential of the third one, and so on. So that means a lot of operations. And on top of that, if each of these terms do not commute with each other, I cannot just split them, of course, because okay. As long as you can hear me, it's okay. So then I will need to, on top of all this representation, maybe apply some Trotter steps or something like that to decompose something like is exponential of this term plus this term plus this term plus this term into small exponentials, which each one will be a quantum gate, okay? So in the end, keep a take-home message, this is a lot of terms, and that's why I mentioned these problem-inspired ansatz sometimes led to a very large quantum circuits. But at least this is a very clever recipe, because I know what are the different steps that I should follow to create all these variational gates, because that's why I include this theta here. So instead of using the theta from the Hamiltonian, like the Hamiltonian term, I use some parameter that I can fine-tune afterwards. So it's my flexibility is added in this way. So then the variational quantum eigensolver is straightforward. It's exactly the same as any other variational quantum circuit. The only thing that changes is the parameterized quantum circuit use a unitary coupled cluster ansatz or another chemistry-related ansatz, and then the expectation value is from the electronic structure problem, because that's the main focus on BQE. And if I use another kind of problem, then sometimes I will call it still BQE, sometimes I will just change the name to variational quantum algorithm, and that's it. So it depends on people, but that's the main thing. So these are some of the examples. For instance, the top one was the Kandala et al. Paper from Nature. This is from IBM. In that paper, they proposed the hardware efficient ansatz instead of the unitary coupled cluster, because the unitary coupled cluster was too complicated to be implemented on real hardware. The first paper of BQE also came with a quantum simulation in a real hardware, in a photonic one, in 2014. So before quantum computers in the cloud, there were people also running these things. And then we also have another example from Google using a hydrogen chains. So all the experimental examples of BQE are with very simple molecules. And for instance, the main authors of BQE, which is Alanas Puruguzik, was one of them, now in University of Toronto. He was explaining to us that it was really hard to publish these papers at the beginning, because these are chemistry papers. And they went to the chemistry journals and said, look, I just simulated with a real quantum computer this very simple example of a molecule, like helium hydrogen molecule and these kind of things. And they say, well, that's completely trivial for classical simulation for quantum chemistry methodologies. And it was really hard because the physical journals, they were not used to chemistry, so they also rejected the paper. So it was complicated. Of course, it ended up being a Nature Communications and not a Nature or a Nature Physics paper, although they tried that with a real quantum computer in 2014, a photonic one. And then you have these other papers that are also great, but all of them are Nature, Science, and so on. So you can see the difference in the field at that time. So that's the problem of opening the path, is that sometimes you don't find very, open referees in that sense. But still, the main problem of BQE now is that if you want a lot of the chemistry accuracy or to simulate large molecules, that means a lot of qubits, that means a lot of terms in your Hamiltonian. So what people are trying to do is to find very efficient representations of these orbitals with this focus space representation. And there are some methodologies in quantum chemistry that can be applied, and people that work on that from the chemistry perspective, they try to find more clever methods to do this mapping and not this direct one between orbitals and focus space. So let me move to the second example, which is the quantum approximate optimization algorithm. Another curiosity here is that this paper was mostly at the same time as BQE paper, like maybe a few months of difference, but it was published on arXiv, and it was never published in a journal. I'm not sure why. I think because one of the authors, which is Fari from Google, they don't care about publish it into a journal, or maybe they received some rejections and decided to leave it on the arXiv. But this is probably one of the examples of the most cited papers that are only on arXiv and not in a journal, unfortunately. But it's a very important algorithm as well. So let me do some preliminaries here, and this is related with adiabatic quantum computation. So as I was mentioning at the very end, my introduction, there is adiabatic quantum computation, which is an analog way to do quantum computing. It's universal, and the main idea is we start with an easy Hamiltonian that we know how to prepare with our quantum computer, And we evolve this Hamiltonian, so we change the interactions of our driving Hamiltonian or something like that, and we end up into the problem Hamiltonian that we want to, make measures on top of it to measure the ground state energy, correlators, whatever. So as long as we fulfill the conditions of the adiabatic theorem, we end up into the target Hamiltonian. So if we start into the ground state of a very simple Hamiltonian, and we change the interaction very slowly, and the definition of slowly comes from the theorem, we can end up in the ground state of the target Hamiltonian. So it's a recipe to create ground states of very sophisticated Hamiltonians that we don't know how to do directly into our quantum computer, but we can kind of evolve towards that solution. So some of the drawbacks of adiabatic quantum computing is that we need an isolated systems, because a change in the Hamiltonian will break the conditions of this adiabatic theorem. So if there is some change that occurs more quickly, then we don't fulfill the adiabatic theorem anymore, and we are not guaranteed that we will end up in the ground state. Depending on the gap, that means the energy of the ground state at the first excited state of the target Hamiltonian, maybe we will need a very long time to do this evolution, so that's also something to keep in mind. And we need an adiabatic quantum computer in the first place, which there are not so many examples. That's why we try to find ways to do adiabatic quantum computation in a digital way, so try to simulate, which is basically quantum simulation techniques. So keep in mind also these preliminaries. So time evolution is from a Hamiltonian that is independent of time. It depends on the Schrödinger equation, as you know. Then trotterization, in case that you don't know, it looks like this. So basically we have some exponential of two terms, of two Hamiltonian terms, H1 and H2. And I can try to approximate that into individual steps, like operation Hamiltonian 1, operation Hamiltonian 2, and so on. And if A and B commute, if these two terms commute, this is as easy as just I stop here. So basically exponential H1, exponential H2. But if they do not commute, I can perform this limit, which means trotterizing somehow the Hamiltonian. So look at this. So this is a limit when n tends to infinity. So in trotter decomposition, there is a coefficient that is called the trotter step, which means how many of these n do you consider infinity. So sometimes it's only one, sometimes it's only two, it depends. Of course, you will make a lot of more errors depending on the trotter step. But once, imagine that I have a 2 here, then it's H1, H2, H1, H2. If I have a 3, it's H1, H2, H1, H2, H1, H2, and so on and so forth. So basically, I'm applying alternatively H1 and H2, okay? Keep that in mind, on intervals of T over n. And then from adiabatic evolution, I just explained that I start with some initial very easy Hamiltonian that I call M, mixing Hamiltonian. Sorry, this is changed. Sometimes it's 1 minus S and S here, but doesn't matter. So, and then I want to end up in the problem Hamiltonian. How? With this coefficient S, which in the case of this formula here starts at 1 and goes to 0. Once I start at 1, I don't have the problem Hamiltonian. Once S is 1, I only have the problem Hamiltonian. And if I change that slowly enough, I end up in the ground state of my problem Hamiltonian. So with all of this putting together, we have the quantum approximate optimization algorithm, which is a variational algorithm as the other ones, and the only thing that is different is what is considered the cost function and how are we computing, proposing the parameterized quantum circuit. So we have some mixing Hamiltonian, which it's called mixing, I'm not sure why, to be honest, but it's an easy Hamiltonian. So it's a trivial one, so it's the sum of all Pauli strings in the x direction, for instance. So the ground state of this Hamiltonian is the plus state, so plus, 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 plus in all qubits. So basically, Hadamard gates on all qubits in the state 0. Something easy to prepare in a quantum computer, and it's a product state. Then we end up our problem Hamiltonian. In the case of the original proposal, it was designed to solve optimization problems. So each of these C's are some satisfiability clause that can be mapped into quantum circuits, and I will not go into details about that, but basically their motivation was that. But it could be now anything that you have some kind of Hamiltonian that is more sophisticated than the original one. So you construct the ansatz by alternating this easy Hamiltonian with the problem Hamiltonian. So you are trying to replicate what happens in adiabatic quantum computation, but with digital operations, so with the individual operations. And instead of putting here the trotter step of t over n or whatever are the coefficients, I open that and I flexibilize this part by introducing these parameters beta and gamma, which are the variational parameters of my circuit that I will need to optimize in the same way as I did with the BQE. So, of course, with QAOA, there is also this parameter of how many of these steps are you using. And the good things of QAOA is that there is some performance guarantees, as happened with also with the variational quantum eigensolver. Why? Because it's inspired by adiabatic quantum computing, so basically you are taking a recipe to create this quantum circuit, and it's not just some bunch of gates that I put here and I cross my fingers that everything work out. There are some theoretical guarantees of this algorithm. You can check it in some of the resources that I wrote before. But the main idea is exactly the same. So the objective function will be the expectation value of my problem Hamiltonian with this particular circuit ansatz. Okay, let me move to the final example of variational quantum computing, which is the one in quantum machine learning, or some of the ones in quantum machine learning. Quantum machine learning is enormous. Basically, there are many ways to think about it, and that's why I like this representation here that comes from some of the papers. So there are two things that could be quantum in quantum machine learning: the origin of the data and the methodology, the type of algorithm that you are using. So if I have classical data and a classical algorithm, is traditional machine learning. If I have classical data, but I use a quantum circuit or a quantum algorithm to process that data, I will call it quantum machine learning. If I have quantum data and my algorithm is classical, some people also call that quantum machine learning, and it appears at the same time, because in the end, I'm applying machine learning to quantum data. But to me, because there is no quantum algorithm involved, I prefer to call it machine learning applied to quantum to distinguish that there is no quantum circuit here in any place, okay? But it's also called quantum machine learning in several papers. So just keep that in mind when you check quantum machine learning papers. What are they talking about? And then, of course, if everything is quantum, of course, it's quantum machine learning. So in quantum machine learning, there are what people do is the same as with classical machine learning. There is supervised, unsupervised, reinforcement learning. So basically, we are trying to find the equivalent in quantum of all the classical machine learning techniques. So let me just focus on supervised learning, which is, I think, the most easy to understand or to explain. So we have, in classical machine learning, we have what is called the neural networks. So neural networks, they have a structure like this. So we have, these are mathematical representations, of course, they are not real neurons. That's why they are called artificial neural networks. So we have some inputs, neurons, then we have the hidden ones. We can have several layers here, and then we have an output. And with this output, so basically each neuron, it's some mathematical function that treats the data that enters into input. So these are some X data, and then you apply some function on this data. And with the sum of all this function applied in each of these neurons that depend on some parameters, I create a final function that is very sophisticated, and this function will be my cost function. And the cost function has to be minimized using backpropagation, using different methods. And with this minimization, I will find the parameters of my hidden neurons, which are called weights and biases. So this is a standard neural networks, standard machine learning. But then how can we do that with quantum? So the idea is I will also have some encoding layers which play the role of the input neurons. So I will need to feed my quantum circuit with the data points. And then I will have some processing steps, which in the end will be some parameterized gates, which play the role of the hidden neurons. Then I will measure the result of my quantum circuit. I will create a cost function, and I will use that cost function to find the optimal parameters in my processing layers or even the coding. So these are called circuit-centric neural networks or quantum neural networks. It depends. There is a lot of issues with the terminology because some people said that it cannot be considered exactly a quantum neural network for other reasons, and there are people directly trying to construct purely quantum neural networks with a quantum response and so on. So sometimes it's an abuse of language. So in this supervised learning scheme, the main idea is I live here in this input state X that is represented in green, and I want to map this into a quantum state. And I call that quantum Hilbert space, and this is called a quantum feature map. So the main idea is I start with some state, then I encode the data, and then I find the optimal rotation to my data in order to measure the final state and create my cost function. So the circuit is divided normally into steps, the encoding part and the processing or rotational part. And once I have this, I can compute the kernel or use standard kernel methods. For those of you that have heard about that, there is the equivalent in quantum, or try to minimize a certain cost function. So machine learning and quantum machine learning is super big field, and there are many proposals to apply that with variational circuits, without variational circuits, and so on. So I think I prefer just to go to a specific example, and then if you are interested on that, you can check references or ask me afterwards. So in our case, we will try to understand how these quantum neural networks can work, and in particular, how powerful they were. So what is the simple but universal classical neural network? If you check the theorems, basically it's a hidden layer neural network. This is not very useful because sometimes this hidden layer contains thousands of neurons, so you don't want that. And that's why people came out with deep learning, which is basically splitting a hidden layer into several ones, and you reduce the resources doing something like this. But technically, mathematically speaking, there is the universal approximation theorem that says that a single hidden layer is enough. So in our case, we were trying to understand what was the minimal but universal quantum neural network scheme. And we discovered that a single qubit was enough for that. But you needed to process the data in a very particular form. So this is explained with this example. So with a single qubit, it's easy to visualize because we can put everything into the block sphere, so we can follow it more intuitively. So if we have some product of unitaries, so as happened with neural networks, I will apply, each unitary will be a neuron, and I will apply one after the other. Of course, I will create something very sophisticated, but at the very end, if I have an initial state and my final state is putting the qubit in a particular position, then I can just go straight there or making something very complicated and end up in the same point. It doesn't matter, because once I train my network for this data point, if I change my point and there is another one here, the unitary transformation will still be the same. So I will end up in the same point. That's not useful at all. So I will not learn anything new. So what I need to do is to introduce some flexibility into this operation that will depend on the data point. So somehow, that's why I call this methodology data reuploading, because I'm introducing the data multiple times along the circuit, not only at the beginning, but multiple times along the circuit, and alternated with some processing unitaries. So the path that moves from one label to another one will depend on the data that goes in, and this path should be optimized to find the optimal one. So once I fed with a new point, I will end up in the correct solution. That's the main idea of data reuploading. So with this kind of schemes, we can do something more and more sophisticated, and it was proven that what you are generating at the end of your circuit is actually a Fourier series. And this Fourier series is universal, and is a universal way to represent functions, and it was another way to prove that these quantum neural networks with circuits are technically universal. So another thing is if we can do that efficient, but at least they are universal, which is the first step. And you can even try to go to multidimensional Fourier series, and it's something that we did recently, and so on, and check what are the requirements. But at least the main point is everything is universal, so at least we can do the same as we did in classical. So let me show you an example, a very simple one. So imagine that we want to classify some points, classical points, to belonging to one class and another class. So I will call class 0 the 0 state, class 1 the 1 state. So if I put a point that belongs to one class, I need to measure in my quantum computer that particular class. If not, I'm making a mistake. We can also create more classes by dividing the block sphere into more points, but that's out of the scope. So basically, my parameterized quantum circuit, as I was mentioning, is the data reuploading strategy, which is some unitary operation that will depend on the data point and will depend on some general parameters that I will need to optimize. So once I create several layers, as more layers I'm creating, the more general will be the function that I can learn. And this is something that I will check easily once I have my loss function. So my loss function is I run my circuit, I obtain class 0, but my initial point was class 1. So I make a mistake. So I create this cost function that will penalize me if I have a mistake. So that's supervised learning. So I have some training set that I will use to check if my circuit is doing things properly. And I will try to optimize the parameters in order to not make any mistake with my training set. And once everything is trained, I will run with new data that is not trained, that doesn't belong to the train set, to test if I perform properly. And this is an example. So we were trying to classify these 4 classes, 1, 2, 3, and 4. And if we use only one layer, you can kind of see that it's trying to make the best, so basically dividing the space into 3 parts. But then if I use 3 layers, the result is much better, and if I use more and more layers, the result will end up with a very high accuracy. So it's a way to construct a quantum classifier. You can find all of these and examples in the GitHub repository that I showed at the beginning. Another example of using supervised learning, but not for classifications, but for function fitting. And you can see here the Fourier nature of all of this. So basically, the only thing that I change for a function fitting is the loss function. So instead of checking the distance between the state that I measure and the target state, I check the expectation value of the, for example, sigma z operator. So the expectation value of this operator will be the image of my function. So if I don't find the correct image, I penalize that with this loss function. So as you can see, if I use only one layer, so the black line is the exact solution. If I only use one layer, I only see one mode, which is mode 0, so constant. If I use 2 layers, I see another mode. If I use 3 layers, I more accurately find the solution, and so on and so forth. So it's another way to see what is the link between this and Fourier series in the end, because you are finding more and more degrees of your Fourier series. This is what's happening here. And finally, let me mix everything that I explained with an example of quantum machine learning applied to quantum simulation, which is this example. What is the true goal of the BQE? So coming back to the original idea of BQE, what chemists were interested about was not about the ground state energy. It was about what is the atomic separation that minimizes the ground state energy, because this is related with the activation energy of my reaction or my molecule eventually. So they did all these simulations, so each of these spots is a different BQE, so something that you need to prepare, you need to optimize, you need to measure, and so on. So it's quite demanding. But in the end, they only care about this particular part, not all these other points, okay? This atomic separation is something that appears in my Hamiltonian. So for each atomic separation, I need to change my Hamiltonian, compute my expectation values, and so on. So in the end, to obtain this point here, they have to run several steps. So how can we avoid to do that? So we can try to use quantum machine learning for that. And that was our proposal, which we call MetaBQE. Of course, this is just an example. There are other proposals as well. But I think it's illustrative to see how can we mix together different techniques. So in the end, I will use training points from my Hamiltonian. This will be the atomic separation, for instance. So I will choose some of them. And I will create a very sophisticated cost function, which means that I encode the parameters of the Hamiltonian into the quantum circuit using the data reloading strategy. And I will try to learn a parameterized quantum circuit that, depending on the parameter of my Hamiltonian, it will end up into the ground state of this Hamiltonian or the other one, okay? So my cost function will be a sum of several cost functions of several ground states for each of the training points of my Hamiltonian. So instead of running individual BQEs, so one for each Hamiltonian, I only run one super big optimization step that contains the expectation value of all training points of my Hamiltonian. So once I have all of these, I have 2 options. The first option is, okay, I just change my parameter of the Hamiltonian without touching anything else, without optimizing anything else, and I measure the expectation value automatically, and technically I should find out the ground state for this new parameter of the Hamiltonian, so I don't need to continue optimizing. Or I can use the optimal parameters as a starting point or something more sophisticated. So one main problem of BQEs was this Barren-Plateau problem, that we end up in some place randomly, and it's really hard to find the direction to continue optimization. But if I start in some point that is close to the solution, then I can end up to the correct solution without suffering from these barren plateaus. So that was, that we call that optimized meta-BQE, and it was just another example of how can you try to put more and more layers of complexity into your quantum circuit to extract the most. And in that case, we mix quantum simulation from BQE with quantum machine learning from the error-blooding strategy. Okay, with that, let me just close all this presentation with why we are working together to go to the HPC quantum integration. So after everything I explained, what happens is we need a classical device close to the quantum device. Because with the BQEs, it's very obvious that this is happening because we need this classical optimization subroutine. But even without the BQE, we need pre-processing, we need post-processing in all possible quantum algorithms. So in the end, we need a classical device next to it for sure. On top of that, I didn't discuss that because I'm not an experimentalist, but to design a quantum computer, to calibrate a quantum computer, you need a lot of optimization subroutines that requires from classical sources, so from classical software. So in the end, you need a classical computer next to your quantum computer for sure. And that's why the main thing that we always discuss if a quantum computer will be better than a classical computer and so on, and this is not the right discussion in my opinion. So quantum computers are not here to replace any other computer. In the same way that GPUs are not here to replace CPUs in all possible settings. So these are specific purpose computers that will be used for specific purposes. So in that case, quantum simulation or solving certain problems that are hard and we know that the quantum computers can be better and so on. But not all possible things. In the same way that we don't use a supercomputer to send an email. We don't need this computational power for that task. So that happens the same with the quantum computer. So I would like to make it clear, at least in all my talks I try to do that, because especially since supercomputing centers are starting to work on quantum computation, it's like we are not here to replace any supercomputer, so everybody calm down. So we are here to introduce a new model of computation that can complement other models of computation. So the main idea, and this is what is happening in supercomputation as well. So you have some algorithm that is sophisticated or requires a lot of computational power, and depending on the application, you may require to use a GPU, you may require to use a CPU, or maybe you will require to use a QPU or even other kinds of processing units, okay? That's the main idea, and that's why supercomputing centers should have different kinds of computers. Because in the end, depending on the application, you will require one or you will require another. And sometimes, in some algorithms, you also need both, or both, or both, you know? So you may require several. And in the case of variational, it's clear that you will need this, at least, and maybe this. So that's what people are trying to understand. So in that sense, how can we do that? So how can we link these quantum computers to classical computers in the first place, which is something that we already do, of course, but even in the future to supercomputers, because we may require even more computational power from some specific task. So this is the workflow that I envision, which is on one side, we have the research. So who is making these quantum computers in the first place? Research labs in universities, in companies, in startups, in many places, as has happened during the last 20 years at least. So of course that these labs build the prototypes, they search for new ways to do quantum computers, to build them, to improve them, and so on. But this is low, what is called TRL, so technology readiness level. So this is a concept that is really important for companies, of course, but also for supercomputing centers, because supercomputing centers are not labs. We are a place where you have a computer that is operational, so you don't need a scientist there doing all the job. You need something that is automatic, and you just manage the basic things like who is having access and who is not. So this is very low TRL because these are just a prototype. So you need someone to take that prototype and scale it up. And this is an engineer problem. Once you jump from here to here, this is physics, this is engineering. So basically, it's okay. I have a very good 5-qubit device, but I need to have 1,000 qubits, 2,000 qubits, 3,000 qubits. So that, of course, there is a lot of physical limitations to that has to be solved here. But at some point, you need someone to make the proper software, to make the proper, managing all the troubles and so on, which is something that belongs more to the industry part, because this is not a scientific, breakthrough here. It's just putting everything in a coherent way. So once I have this something with higher TRL, then I can go to the shop and buy a quantum computer, basically. So the main idea is that here you need the deployment. So who will have access to these quantum computers, and who is the owner of these quantum computers? And replace quantum computers with supercomputers, and you will end up with what is happening nowadays with supercomputing. So basically, the idea is you have some research centers that have these very powerful supercomputers or very sophisticated devices, and offer this access to any user that is interested or needs to use it. So supercomputing centers in general are public institutions that we offer this access for free, basically, to all researchers and people that wants to do research. And then, of course, you can find companies, you can go to Amazon, you can go to many places where they have this supercomputing power as well, but then you pay as you go, or you have some agreement with that, and that's what other companies do. So, of course, these two models are compatible with each other, and the main idea, and we are here. So we are public research institution at the BSc. We offer supercomputing power. We have the most powerful supercomputer in Spain, and in a few weeks, I think, one of the most powerful supercomputer in Europe, which is called Mare Nostrum. And the main idea is, okay, now we want to increase our capacity with having a quantum computer, even if it's a prototype, even if it's something that it's just for research and it's just to see what are the power of all of this. But we want anybody, at least in Spain and of course also in Europe, to use this device for free and just to see how it works and learn how it works and try to find applications and so on. So this is the main goal of quantum computing infrastructure at Barcelona Supercomputing Center. We are also the National Supercomputing Center in Spain, and that's why we have these very big projects as well. So on one hand, we have Quantum Spain, which is the project that I'm coordinating. These are 22 million euros budget from the recovery funds of European Union, and it goes to all Spanish supercomputing networks. So the Spanish supercomputing network is made of 14 institutions now, and all of them have supercomputers, and they share the computational time with all the networks. So you just go there, you ask for some computational time, you submit your project, and you have access, the remote access to the supercomputers. So the main idea will happen with the quantum computer that will be located at the BSc. It will just belong to this network. So basically, we are sharing this quantum computing time with everybody interested. So, and then we have the other project, which is the European one, that is called EuroQC as Spain, for reasons that I will mention at the end, which has a budget of 12.5 million euros, and it comes from EuroHPC, and now I will explain a little bit more. But the main idea is, in this case, the participating institutions are BSc, ENL in Portugal, and IFAE in Barcelona, and we will have a second quantum computer that will be compatible with the Quantum Spain one. So let me go very quickly of the lines of work of Quantum Spain. So we have 4 lines of work. The first one is, of course, having the quantum computer. The second one is having access to this quantum computer from all users in the Spanish supercomputing network. And for that, there are several technicians across all these institutions that will help the users in a sense that solving issues and trying to make them work on these devices. And I think here in the audience, at least I see 2 of them, which is from Zaragoza, Sergio and Raúl and also Jaime from Madrid. So you can talk with them later. And then we also do research, because in the end, this is something that is under research. What kind of quantum algorithms can we run? And here the main idea is we will collaborate with several institutions in Spain to develop algorithms and to study science with them. And finally, it's training. And training, an example of training is, for instance, something like is happening here today, so trying to work with anyone in Spain that wants to develop and show some and organize meetings. So the quantum computer, very quickly, it's based on superconducting circuits. We make a public procurement process that was acquired by Kilimanjaro and GMV, which is another company in Spain. But all technology is European. So all the chips are made by IQM, by Quantware, and then the electronics by Qblocks, the dilution-free slide and cryogenics, and so on. Now we have access to this quantum computer, and we are trying to, we are now understanding how it works, and we are making some tests. And if everything goes right, at the end of this year, beginning of this next year, it will be installed at the BSC, so everybody will be free to visit it. And we will also open the access to everybody interested. And in the European context, what is happening is it's being created an European quantum and simulation infrastructure. So basically in Europe, there will be several quantum computers and simulators, and everybody will have access to these devices. And this is called EuroQCS. And because of that, EuroHPC, which is the branch of European Union that focus on supercomputers, now they say, well, now it's time to also focus on quantum computers and install these devices in supercomputing centers. And that's why it was selected 6 sites across Europe, and one of those will be in Barcelona in Spain. And this is the EuroQCS Spain project. And we will have the digital quantum computer that comes from Quantum Spain. We will ask to EuroHPC for an analog quantum processor, so we have 2 different kinds of computers. And all of this will be integrated into Mare Nostrum 5 Prexascale supercomputers. So basically, anybody that comes remotely, of course, to BSC, they will have access to all this infrastructure. And this is something that we do in collaboration with Portugal. And the other supercomputing centers in Europe, they will have other kinds of quantum computers. We are also collaborating with them. So everybody in Europe have access to all kinds of technologies, and we will be able to test different kinds of technologies. And with that, these are the conclusions of my lecture today. And my main goal is to just please enjoy these exciting times, because now it's a really exciting time for quantum computing. I started in this field before, right at the transition when it started to become more and more relevant, and it's very exciting to see that we can do all this science with real quantum devices. That was something unimaginable a few years ago. So it's very fun to work in this field. So thank you very much for your attention. Happy to answer any questions.
Okay, thank you, Alba. For the sake of time, we have time for maybe one quick question. Does anyone have a question?
Unfortunately, I have to leave this afternoon, but I will stay all day, so in case you have questions in the coffee break or during lunchtime. Or you can just drop an email as well.
Thank you. Can you hear me? Yeah?
Yeah.
Thank you very much for this talk. I'm actually a bit interested on how much interaction there is on the experimentalist co-design of this type of systems that you're working on, say in Quantum Spain, or with the European projects. How much back and forth is there for improving the type of systems that you build and improving the algorithms that you can implement?
So very good question, because our problem to this back and forth is that it comes from the legislation. So we had to make a public procurement process, which means that I need to specify what I want, and once everything is set, we cannot change that, okay? So this is not the same as having a collaborative project, where things can change, we can negotiate things, and so on. So here we cannot negotiate anything. So everything is set. So that being said, of course, there are many things that are not specified that we'll need to discuss. So for instance, we asked for a quantum computer of 5 qubits, and then we will end up with 30 qubits at the end of the project. So these are the steps that should be followed. But of course, in the middle, it's open to discussion of other things, like, okay, the software is this particular one, and this is set, but maybe we can add another layer, or maybe once I start using the quantum computer, I find that something is not working properly for some reason, or not as good as I was expecting, although it's not written anywhere. So we can, of course, discuss. So what I can assure is that we communicate with them, of course, and we are trying to extract the most, because everybody's interested to make it work. In our case, because we want to offer the best services to users, and in their case, because they want to offer us the best service, because that proves that they can do that properly. And the same will happen with the European one. So of course, there are other projects that are beyond this, which is research projects that you can work together with companies to develop technology, and that's completely different. But again, coming back to my different steps, we are in the final one, and the final one is something operational, so it's not up to discussion as much as the first one, of course. So I think that these are two different things, and we are acquiring technology that is ready for deployment. That doesn't mean it's the best technology possible. The best technology possible is still in the labs with people that know properly how to use it. So we will just wait until this technology comes as well.
Okay, so with that, going to the coffee break, we have to move to another building, so we'll lead you there, and we'll reconvene here at 11:30, okay? Thanks a lot, Alba, again.
Thank you.